Welcome to The Explainer. We're all about taking complex topics and making them, well, simple.
So let's jump right in. Take a look at this tree. How would you count all its nodes? The obvious way, right? You just start at the top and go 1, 2, 3, easy peasy. But what if this tree wasn't so small? What if it had millions or even billions of nodes?
And that's where the real puzzle comes in. See, the challenge we're tackling today is to count all those nodes, but, and this is the kicker, we have to do it without visiting every single one. We need a shortcut, a clever hack that's way faster than just brute forcing it.
So this is what we're calling the counting conundrum. And really, it's not just about counting. It's about being smart. The key is that the tree we're dealing with isn't just any random tree. It has a very specific structure, and those rules, well, that's where we're going to find our shortcut. And that special structure is called a complete binary tree. Now, don't let the name scare you. It just follows two really simple but really important rules. First, every level is totally packed with nodes, except maybe the very last one. And rule number 2? On that last level, all the nodes are jammed over to the left side as far as they can go. That's it. And that structure, that's our big clue. Okay, so here's the big rule we have to follow, our one major constraint. Whatever we do, it has to be faster than O of n. Now, what does O of n mean? It's basically the visit every node approach. The time it takes grows in a perfectly straight line with the number of nodes, n. You double the nodes, you double the time. We're not allowed to do that. We have to be way, way more efficient. We have to beat that linear clock. So before we get to the clever solution, it's always a good idea to look at the simple but slow way of doing things. To really understand the problem we're trying to solve and what we need to beat. And that simple way is, you guessed it, recursion. It's actually a pretty elegant little piece of code. The logic is like this. Hey, if I'm a node that doesn't exist, my count is 0. Otherwise, my count is 1 for me, plus whatever my left kid tells me their count is, plus whatever my right kid says. It's like a chain of command, passing the question down the tree until everyone's been counted. And this really highlights the classic trade-off, doesn't it? On one hand, it's super simple to write, easy to wrap your head around, and hey, it gets the right answer every single time. But, and it's a big but, its fatal flaw is that it has to touch every single node. That makes it ON, which means for our specific challenge, it's a fail. We have to go back to the drawing board. All right, so how do we get faster? If we can't visit every node, what can we do? Well, the secret, the key to the whole thing is hidden right in the definition of the complete tree itself. We've got to exploit those properties we talked about.
To do that, let's first look at a slightly different kind of tree, a full binary tree. Think of this as the perfect tree. It's perfectly symmetrical. Every node either has 0 children or exactly 2 children, all the way down. And the last level? It's completely packed. No gaps, no missing pieces. It's full.
And here is the magic of a full, perfect tree. We don't have to count the nodes at all. We can calculate them instantly. There's a simple formula. 2 to the power of the tree's height, h, minus 1. Bam. Done. If you know the height, you know the count. No visiting required. This is the powerful shortcut we've been looking for. And right here, this is the big aha moment. Our complete tree, the one we're actually trying to solve, isn't perfect, like a full tree. But, and this is because of that filled from the left rule, it is guaranteed to have a big, perfect, full subtree hiding inside it. And if it's full, that means it's calculable. Our mission then is to find that perfect piece. All right, let's take that aha moment and turn it into a real wicked fast algorithm. This is where the theory becomes practice. So, the new question is, how do we actually find that hidden full subtree without wasting a bunch of time? And how can we use our formula to speed everything up? We need a really quick test, a way to just glance at a part of the tree and know, yep, that part's perfect. And the trick is surprisingly simple. From any node, you just measure 2 things, the height all the way down its leftmost path and the height all the way down its rightmost path. Now, if those 2 heights are exactly the same, bingo, you know for a fact that the left subtree is a perfect full tree. If the left side is taller, that means the right subtree is the perfect one, just 1 level shorter. That simple check tells us exactly which chunk of the tree we can use our formula on. And this is the whole game changer. Think about it. Instead of going node by node, we look at a huge section of the tree, say the left side, and we go, that's a perfect subtree. We use our 2 to the h formula to calculate all its thousands of nodes in one shot, add that number to our total, and then we only have to recursively explore the other, much smaller side. We're literally chopping the problem in half, or even more, at every single step.
So what's the end result of all this cleverness? Well, we make a massive leap in performance. We go from O of n all the way to O of log squared n. Now, what does that mean in plain English? At each step, we're cutting the number of nodes we have to think about down logarithmically, just like a binary search. But to make that cut, we have to calculate the height, which is also a logarithmic operation. So you get a log operation inside another log operation, hence log squared. It's not just a little better. It's in a completely different league of speed.
And the difference is just staggering. I mean, look at this chart. The simple O of n approach is that line that just keeps going up and up. But our optimized solution, that line barely even budges. For a really big tree, this is the difference between getting an answer instantly versus going to make a cup of coffee, or maybe lunch. And this really gets to the heart of a huge idea in computer science. It's not about brute force. It's about deeply understanding the structure of your data. When you exploit the specific properties of a system, you can often find these incredible shortcuts that make your solutions orders of magnitude more efficient. It's about working smarter, not harder.
And that's what I want to leave you with. Think about the problems you work on. Where else is there a hidden structure, a set of rules that you could use to find a shortcut? What other complex problems could be simplified if you just looked at them in a slightly different way?